Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. The course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We are both from the Civil Engineering Department of IIT Kharagpur. We have divided this course into two parts, Environmental Chemistry and Environmental Microbiology. The first part, environmental chemistry, will be covered by me, and the second part, environmental microbiology, will be taught by Professor Sudha Goel. I was explaining the chemical kinetics in my previous lectures. This is the module 3 and in module 1 I have explained acids, bases and salts. In module 2 I have explained the chemical equilibrium, and this is my 14th lecture which will discuss the chemical kinetics. Now, in this lecture I will tell about the effect of temperature on rate of a reaction and pseudo first order reaction. Now, I already told you that the specific rate constant, that K. One thing I must tell you at this point, that equilibrium constant and specific rate constant, hope that you have already noticed that in chemical equilibrium, the K value, that is the equilibrium constant, I always expressed in terms of capital K, and in the rate expressions, that specific rate constant I always written in terms of small k. Okay. So, in many books I have observed that this is not maintained, but this is a good practice, and it should be always maintained that for equilibrium constant we will use capital K, and for rate constant we will always use the small k term. Now, I already told you that the equilibrium constant and both equilibrium constant and the specific rate constant, they depend on temperature. So, how does it depend, means what is the effect of temperature on the rate of a reaction, that I will tell. Now, it is known that when some reaction goes on, the molecules has to collide with each other. Okay. In case of small molecules, say for example, the collision frequency, that means the number of collisions per unit time is very large. Okay. And if we think that the collisions, each collision will give rise to reaction, then it will not match. In many reactions we see the rate is much lower compared to the number of collisions per unit time. So, the question is coming that all collisions give rise to reaction or not, each collision will produce reaction or not. Okay. So, this is a question. No, it is not. All collisions do not give rise to reaction. Okay. Some reactions means some molecules. Another thing is important, the molecules to react or to give some product. Okay. It needs some orientation, some specific orientation is needed. The collision should occur in some specific orientation. I am giving a simple example here. I have shown a simple example here. So, for example, NaCl. NaCl is decomposed to NO and Cl2. Okay. So, here we can see that if we write in this fashion, then we will see that there is the bond between nitrogen and chlorine. Okay. And the product, this is the chlorine bond. So, this bond has to be broken. Okay. And this bond between two chlorines, that is the bond should be created. Okay. If this has to happen, then how the collision should be, what means three dimensional, if we think that what is the orientation of collision. See here, it is the C, this is the chlorine. You think about this molecule just in this fashion. This is the chlorine, this is the nitrogen and this is the oxygen. This way, this is the chlorine and this is the nitrogen and this is the oxygen. Now, if they collide in this fashion, that means chlorine, this chlorine atom is away from this molecule. Okay. If they collide, then reaction will not occur, okay, because chlorine bond formation is required to get the product. So, the orientation should be like this, okay. And if this type of collision occurs, then chlorine bond formation will happen to give the chlorine and NO will be formed. So, we have seen that there is another factor, it is called steric factor. Is there any other factor? Even we can think that if the molecules collide in proper orientation, then also all collisions should not give rise to, may not give rise to product. Then what is the other factor? Is there any other factor? Is there temperature? Is there some energy, some critical energy? That is our discussion, okay, topic of discussion, okay. Now, it has been observed that the rate of reaction increases extremely rapidly with increase in temperature. So, rate increases. It is known that it is, we can think easily that when the temperature is increased, the molecules will run in a fast way, means they will run fast and they will collide more, that is okay. But is there any other effect? That is the thing. So, Van 't Hoff rule, it is the Van 't Hoff rule, where it is said that it is approximate rule though, it is said that the reaction rate doubles for a 10-degree rise in temperature. This is observed thing and this is approximate, this is not quantitative, this is approximate thing. So, per 10-degree rise it is observed that the rate doubles, okay. So, this is some observation. Then in 1887, Arrhenius suggested that the rate constants vary approximately, varies exponentially with the reciprocal of the absolute temperature, and he gave this expression K, this is the rate constant, equals to A, this is known as Arrhenius factor, and e to the power into e to the power minus A by RT. R is the universal gas constant, T is the temperature in absolute scale, and A is the some energy which is called activation energy. So, this is given by Arrhenius in 1887. Now, if this is the expression, then it is obvious that A, Arrhenius factor, will have the what is the unit. So, and what is the unit of EA? EA has the units of energy per mole. EA is called activation energy and it has the units energy per mole, and Arrhenius factor A is an empirical parameter that has the same unit as K, okay. And this one, if we take the ln both sides, then we will get ln K equals to ln A minus EA by RT, okay. This is the expression by taking ln. So, from this expression we can tell that if we plot ln K versus 1 by T, ln K versus 1 by T, because here is the negative sign. So, we will get a straight line like this with the negative slope, okay. Slope EA by R, slope is the EA by R, and we can get ln A from the intercept also, okay. So, what we will do? What we will do? We will do the reaction, same reaction we will do at different temperatures, say 4 or 5 different temperatures, we will do the same reaction and we will determine the K value. K, what is K? K is the rate constant. Okay, we by now we know how to determine the rate constant, what is the what is the order of the reaction, how to determine the order, all those things we know. But then after determining the K, we can plot ln K versus 1 by T. So, we will get a straight line. From the straight line we will get the activation energy EA, okay, and also Arrhenius factor. So, this is a very good experiment to determine the activation energy. Okay, activation, what is activation energy? Now, activation energy is some type of energy which the molecules must possess to do the reaction. Okay, to do the reaction means not only the collision, number of collision, it is important, but it is not the only one. So, number of collisions, that is frequency, collision per unit time, this is a frequency, and then important is the steric factor, and then some energy is also required, means some energy also needed. This is the critical energy, okay, to get the reaction. So, Arrhenius believed that for molecules to react upon collision, they must become activated. And the parameter EA is known as the activation energy. This is Arrhenius believed. Okay. His idea also extended or refined by further by other scientists such as Marcelin 1950. He also said that all collisions do not give reaction. Okay, those collisions whose collision energy exceeds some critical value can lead to reaction. This is the main thing. So, collision energy should exceed the activation energy. Okay, then it is they will produce some reaction, they will give the reaction. Okay. Now, here in the curve you can see, although here it should be little smooth, it is handwritten, so hand drawn, that is why. It is the Boltzmann-Maxwell distribution curve of the molecules. So, this is at T1, this is the distribution at T1 and this is the distribution at T2. Here it is spreading, this curve is spreading. Okay. And now, T1 is T2, this is T2, T2 is larger than T1. Okay. Now, this is the EA, say for example, this is the activation energy. So, what you see that in case of T1, the number of molecules that is possessing the kinetic energy higher than EA is much less. Number of molecules that is having higher energy than the EA is less compared to the number of molecules having the higher energy than the EA at T2. Okay. Here number of molecules are higher, that is why these molecules will give rise to give the reaction. Okay. So, reaction rate increases. Okay. Now, this is the some concept. Okay. Now, what is the pseudo first order reaction? You already know the first order reaction, but what is pseudo? Pseudo means false. We know pseudopod, pseudo means false. Now, pseudo first order means it is false first order. Okay. So, let us see an example. Consider an example A plus B giving P. Okay. This is an example. Here B is present in large excess, in great excess over A, compared to A, B is present in large excess. Okay. Then we can say that there is almost no change for B. Okay. Initial and final, there is almost no change in B. Okay. Then during the course of the reaction, therefore, the concentration of B can be considered as constant. Okay. B is not means affecting or contributing. Okay. So, then in that case we can tell actually it is a second order reaction. If it is first order with respect to A and first order with respect to B, then it is a second order reaction, overall reaction is second order. but because B is in very large excess, so we can consider that it is only proportional to the concentration of A. That means it is first order with respect to A, okay, but it is not actually first order. Overall reaction is not first order. That is why it is called pseudo first order reaction. Okay. In that case, if we express the means if we write the rate expression, then it will be dCA dt, because we are considering only A. So, dCA dt, this is the rate of the reaction, it will be K into CACB, although this is the actual, but CB is constant. So, K into CB is also another constant, and that is we have written K observed, okay, that we see experimentally, that is K observed. So, dCA dt, this is the rate, is nothing but K observed into CA. Okay. So, this is the first order. Now, you can ask that if I really want to know the second order rate constant, that is we want to know K into CB value, then what we will do? Means we want to know the K value, this is the actually second order rate constant, right. So, if we want to know actually the second order rate constant, then what we should do? K observed is the pseudo first order rate constant, but if I want to know the second order rate constant, then what we will do? It is not needed, but you can ask what we will do. Then what we will do? We will determine the K observed at different concentrations. We do the reaction at different concentrations of B. So, we will vary CB, okay, and we will determine K observed. Then we will draw a curve, and then from there from the slope we can determine the K. This is the second order rate constant. Okay. So, we understand that pseudo first order reaction, basically it is a second order maybe, but because of the presence of large excess of one component, we can consider that the concentration of that component is not changing. So, basically it is the first order reaction with respect to the other component, other species, that is A here. Okay. There are many examples of pseudo first order reaction, and many of them are very important reaction. Say for example, the example, it is also called pseudo unimolecular, because you have seen here, it is the, if this is the equation, then here 1 mole is involved, that is why unimolecular. Okay. And by chance it is also first order also, we have explained in terms of first order. Okay. Now, ester hydrolysis, you know what is ester. Okay. Ester is a substance that is produced from an carboxylic acid, and alcohol, okay, by elimination of water. This is a condensation reaction between a carboxylic acid and an alcohol. Okay. So, ester, when it is hydrolyzed in water, okay, then water is present in very large excess, okay, and in that case it is decomposed again to acid and alcohol. So, but because it is present in a large excess, that is why even if it is a bimolecular reaction or second order reaction, but still it is a pseudo first order reaction, and it is only dependent on the concentration of the ester. But it can be made, the same reaction, it can be a second order reaction if some alkali, it is here there is no alkali, but it can be made alkaline hydrolysis, same material, it is also ester, but hydrolysis is done in presence of alkali. In that case, alkali is taking part, alkali is not excess, water is excess, but alkali is present in low concentration. Okay. This is some type of catalyst, alkaline hydrolysis. Okay. Then this reaction is no more pseudo first order reaction, in this case it is second order reaction. And there is another example, you have learnt in the acid base salt. Here say for example, you do the reaction in another solvent, okay, in another solvent, but for the hydrolysis some water is required, because you know that lysis, what is the meaning of lysis? Lysis means breaking, okay, like photolysis, using photon you are breaking something, thermolysis by using heat you are breaking something, okay. Electrolysis, by passing electricity you are breaking something. So, lysis means breaking, okay. Hydrolysis means it is breaking of some molecules by using water. So, here you see by using water you are breaking this molecule, okay. Now, if you want to break this molecule in another solvent, it is not water but another solvent, but to do the lysis, to do the breaking, you use little amount of water, okay. In that case it is not in large excess, in that case it will not be in pseudo first order. In that case water concentration also you have to consider, okay, and that case it will again be means bimolecular, or it may be second order reaction. So, depending on the condition it will vary, okay. Now, this is another important reaction, this is the inversion of cane sugar. You know cane sugar is sucrose, cane sugar is sucrose. So, if you by polarimeter you can measure the optical rotation. You may not be very familiar, but chemistry people they are very familiar with this reaction, and the dextro rotation, starting with dextro rotation, dextro rotating molecule you can get back levo rotating molecule. That is why it is called inversion of cane sugar, okay. You are getting molecules which is glucose and levulose. So, these two molecules finally will give the inversion, means optical rotation will be changing. So, I am not going into details. Now, these are the examples, okay. Now, second order reaction, you see I have given this example for chemical equilibrium. I have said that hydrogen and iodine in gas phase reaction produces hydroiodic acid. Maybe 444 degree centigrade, hydrogen and iodine if you mix, it is a gas phase reaction, both are present in gas phase, then it will give hydroiodic acid. So, you will get some percentage conversion if you allow the equilibrium, okay. Now, if you start with HI also you will get, this is not in this chapter, but just I am telling, just remembering that. But this is, you see, this is one molecule, this is one molecule. So, it is a bimolecular reaction, at the same time it is a second order reaction. Here also there are no two species are not present, but only one species, but two molecules are involved, okay. That is why it is also bimolecular reaction, this is also bimolecular reaction, okay. This is basically opposite reaction, you see here hydrogen and iodine giving hydroiodic acid, here hydroiodic acid is giving iodine and hydrogen, okay. So, this is a good example of second order reaction. Third order reaction is there, but not very common, but third order reaction, this is also this is an example of third order reaction, and this is also termolecular also, because 3 molecules are involved, 2 NO molecules, 1 Cl2 molecules. So, termolecular. So, it is also third order reaction and termolecular reaction. So, there are many examples, only a few examples are shown. Now, for this type of means this, for this concepts you can get from same books that I mentioned in the earlier lectures, same books you can get, you can read more, okay. Thank you.